Here's another video in which we derive a formula to express the rotational inertia of a particular shape about a given axis. Here the shape is a hollow sphere, otherwise known as a spherical shell, and the axis shown is an axis that passes through the center of mass. So I'll cut to the chase and give you the final result. Turns out the rotational inertia is equal to 2/3 times the total mass of the spherical shell times its radius squared. Okay, but now we have to explain where this comes from, and this is probably going to be one of the longest derivations that we encounter, but it's worth taking the time to go through it, as it'll help you relate to how we apply the general definition of rotational inertia as I equals the integral of r squared dm. And as always, we need to picture what we mean by dm. So let me show you how I picture dm in this case. I suppose I could make a complete hollow sphere by putting together a bunch of rings like this. There's my first ring, and then I've got a second ring with a slightly smaller radius here. Hopefully that doesn't look too messy. In general, you'll have some ring up here that looks something like that. Now, the radius of my sphere is capital R, so whether I'm looking at this ring or this ring or anywhere, right? These are all R and R, but that's because I'm measuring from the center to the perimeter. But what if I measure outward from the central axis to the perimeter? So I'm measuring a distance this way. Okay, that distance is a smaller value, and I'll call it lowercase r because each ring has successively smaller and smaller values of this lowercase r. I'll probably end up drawing this again because I've sort of made a mess out of it. So here we go. Step number 1, and let me do just that. Let me draw our spherical shell one more time. Draw it even bigger. All right, it's got some non-zero thickness, yet that thickness is much, much less than its radius. All right. That's the axis of rotation. I'll also draw some x-axis. And let's pick just one of these rings that can be banded together to make one complete spherical shell. Here we go. Okay, there it is. So if the entire hollow sphere has a mass of capital M, then this ring that makes up a fraction of the total mass is the dm that I'm referring to. And as far as the dimensions are concerned, that ring has a radius of lowercase r. However, the distance from the center of the spherical shell to the edge of the sphere where this ring is located is a distance of capital R. I see an angle here, and if I were to drop a line down, this distance is the same as this distance, so I have a right triangle with a side adjacent to the angle of lowercase r and a hypotenuse of capital R. That's going to be important in one of the substitutions we make at some point in this derivation. In any case, moving on to step 2, I equals the integral of r squared. Now I need to make a substitution for dm. And once again, density is the key. In this case, instead of density as a measure of kilograms per cubic meter, let's talk about area density as a ratio of kilograms per square meter.